Hello everyone. So now that we have a very well defined structure for the NMOS circuit description, so we came up with this particular description of this netlist, and that's very well defined. Well understood by the Spice engine. The next step is to get the model for this particular NMOS. So model, you can think of something like AND gate. An AND gate has a model where it says that output is a Boolean multiplication of its inputs. For an OR gate, the output is a Boolean addition of your inputs. Similarly, this NMOS will also have its own models. And I had introduced you to the models in some other videos, and we'll revisit them over here as well. So this NMOS, when we plug in the models for this particular NMOS, the Spice engine very well understands that where this NMOS has been picked from, what are the constants that has to be taken for NMOS, and eventually evaluate the threshold voltage and the drain current equations for that particular NMOS. Okay, so let whatever we said, let's try to do it practically over here. So sometime back we had introduced you to the model parameters. So we said these are the models of NMOS. So for example, we have this VTO, which is needed for the VT calculation. We had this gamma, which is again needed for the VT calculation. So once you have these constants VTO, gamma, and Kn dash, and lambda, and some more, you have this Cox, you have epsilon SI. Once you have all these constants, it becomes very easy to calculate the models VT, ID, and ID in the linear region, and ID in the saturation region. It becomes very easy to calculate all of them, and these values will be used by this MOSFET when we try to simulate this particular MOSFET. And that's the whole idea of having the model files. So that's basically model files. You need some model parameters. These are your model parameters, and these are your models. VT is a model of NMOS. ID is the drain current in the linear region. This particular equation again is a model of your NMOS. The drain current equation in the saturation region again describes your NMOS. Okay, so that's basically model. So to evaluate these models, you need some model parameters, you need some constants, you need the values of this particular constants. Not only that, you need the value of this particular constants for this technology node. Okay, so 1.2 micron, you go to the foundry, you ask for the technology parameters for 1.2 micron, and you will get it. Okay, so these are few things that you need as an input for the Spice engine, and that's where the technology file comes into picture. So for example, if we were at a lower node, some different node, let's say 250 nanometers or 350 nanometers, the model files, the model parameters for them will change. Okay, and the model equations that we have introduced over here for 1.2 micron, they fairly remain the same for lower nodes as well. But for lower nodes, there are something extra, more amount of accuracy that gets added into the models itself. So we'll come to that accuracy part when we go to lower nodes, and we will be going to lower nodes. The next node that we'll be trying after 1.2 micron is 350 nanometers. So just stay with me. Okay, so these are the model parameters, and all these model parameters comes as a package. So the way you describe these model parameters are something like this. You give an attribute dot model, you call it a name NMOS, and this name should correctly match with what you have in your netlist. So NMOS, if this has been described as NMOS, this NMOS, the models for this NMOS, or the model parameters for this NMOS, will be taken from let's say a file which has this attribute. If you don't have this, and if this name and this name are different, things will go weird. So this is a very important step that most of us miss, and that thing is, this NMOS should match with the NMOS name over here. Okay, that's the most important thing. Similarly, if we had a description for PMOS, the name used in this circuit for PMOS should exactly match with this particular PMOS. Okay, and that's what this slide describes. So once we have this attribute in this fashion, we have dot model. It says NMOS, and now this is the technology, the foundry name this is the name that foundry gives to the NMOS. So NMOS, and you have all your technology parameters defined over here. I'll come to how do we define it. This is the way you do it. So this is dot model NMOS, the capital NMOS, and TOX is your constant. So for example, let's say COX is epsilon ox by TOX. So that TOX is being given over here. Okay, the the VTO over here, which is the threshold voltage in the absence of VSB. This is how you describe VTHO in the standard model file. Okay, mu naught again comes when you expand Kn, you get the mu naught, and this is how you describe mu naught. It's called U0. gamma 1. So this is your gamma value, which is the body effect coefficient, and this is how you describe it. So once you give gamma 1, the engine will automatically replace symbol of gamma with this gamma attribute and evaluate this equation. And this equation will be provided to this equation, and your threshold voltage will be evaluated. So this is how it works. You need to provide all the constants in a file, and the engine will evaluate all these equations, all these models for you, provided you give the correct inputs. So we are done with the models, where model is the ones which is used to define these constants present over here, and this will be used by the engine to evaluate the drain current in the linear region, in the saturation region, the threshold voltage, and so on. Similarly, you will have something for PMOS as well. Okay, and when we have a circuit with PMOS as well, so at that point of time, this makes more sense. For this, you don't even need the PMOS, but let's keep it for completion. So you will have the description for PMOS, you have the description for NMOS, which will be used over here, and then the final step is basically you have to provide the inputs of your gate voltage and drain voltage. I'll come to that. Before that, let's try to conclude on this. So there is a huge list of this model. So if you actually open up any of the technology file, which I will be uploading in on this as a lecture side note. So when you open up that particular model file, the list is pretty huge, and I'll bring up a video on which we will be explaining each and every model parameter. It's a bit complex, it's a bit side lecture, so that will be on advanced physics, on advanced semiconductor device physics. So I'll be introducing you to those models. For now, let's stick to this particular model files, because that's the one basically we need for our purpose. Okay, so the list is huge. So you package all of them into a single file. First of all, we need to give a name to this one. Let's say we will say that these are .lib CMOS underscore models. The name of this particular of this particular models are given. This is the start and this is the end point. So .lib CMOS underscore models will very well describe this particular file, and you can have other models as well. So it can go on. Okay, and now you just plug in this particular, you just package this model files into a .mod file, and call this .mod file in the top level netlist, something like this. You say .lib xxs.mod. This is nothing but the model file which has all the NMOS and PMOS model parameter description, and CMOS underscore models is this section in that particular .lib that we need to pick up. After that, it goes over here, it gets the correct value of NMOS, and the NMOS model parameters are being plugged, and the equations are evaluated, and these models are evaluated. Okay, so this was, let's try to, this is your complete, this is the one of the complete spice deck we have. So let's try to give some names over here. This will be called let us call the first section as netlist description. Okay, let us call the below section as dot include. So just a name. Whenever anything starts from asterisk, that's a comment in a spice netlist. Okay, so this won't even be recognized. This is just for your description. So you have netlist description, which is this section. You have the model file description, which is being coming from this section, and the next is to add the simulation commands. Okay, so by simulation commands, when we say simulation commands, is basically the way you provide your voltage levels. So in this case, we have two voltage levels. We have the gate voltage, which is 2.5. We have the drain to source voltage, which is again 2.5. But for simulation, we need to sweep the drain and the gate voltage. Because why do we need to do that? We had come up with a question sometime back asking us that we have done this evaluation of the drain current using hand calculation, using at a single value of VGS. But if we want to do it for all the values of VGS while sweeping VDS from 0 to the supply voltage, how do we do it? And the answer for that was spice simulations. Makes it very easy. So we'll try to use the spice simulations while calculating the drain current for our MOSFET that we were looking into. So since I'm already running out of time, we'll add the simulation commands. We'll give some commands that will help the Spice engine to say that the VGS has to be swept from 2.5 volts. The VDS has to be swept from 0 to 2.5 volts. So we'll add those commands, and let's try to do the complete Spice simulation in the next video. Thank you.